Hello mathematicians, thanks for joining me as we look at more calculus over polar curves. And so what we're going to do is we're going to look at the curve r equals 3 sine of 4 theta, and we're going to find the slope of the tangent line for a given theta. That is, we'll find the derivative dy dx with respect to theta, and then we're going to find, based on this polar curve, what is the area enclosed by the curve. So now in order to do that, what we want to do to start with is we want to get a graph of the function so that we know what it looks like and what we're actually trying to find. So then we'll go ahead and do that. Alright, so in order to get our graph of r equals 3 sine of 4 theta, we're going to start off by graphing the function y equals 3 sine of 4x. That is, we'll graph y as a function of x. Now the reason why we're going to start that way is because we should know how to do this because we know what sine curves look like. And if we have a 3 out front, that just means the amplitude is 3. The 4 on the inside gives us an amplitude of 2 pi divided by 4, which would be pi over 2. And so we can plot this one out fairly quickly. And what we get is that, well, if I plug in x equals 0, I get y equals 0. At pi over 4, I get sine of pi, which is going to be 0. At pi over 2, I again get 0, 3 pi over 4 is 0, pi is 0, 0. And so at each multiple of pi over 4, we're going to get sine of 4 times a multiple of pi over 4 is just sine of a multiple of 5 is 0. And so I get all those points are 0. Now, if I look at in between to try to get a better graph is at pi over 8, I get sine of pi over 2, which is 1 times 3 is 3. And then between pi over 4 and pi over 2, halfway between, I would have negative 3. And so I can just draw, okay, well, sine is going to go up and then down, and then it's going to go back and forth. And we're going to oscillate all the way until I get to pi, or 2 pi. Now the reason why I graph this out from 0 to 2 pi is because when we're graphing our polar curve, we're going to have theta starting at 0, and we're going to go all the way to 2 pi. So if I plot from 0 to 2 pi, I get all the information I need to be able to graph my polar curve. Alright, now that we have our regular function done, we now want to plot our polar function. So the idea is that we're going to look at this and say, well, at 0, so theta is 0, r is 0. So if I plot that point, I have theta is 0 here. So r is 0 would correspond to the point 0, 0. Now notice what's going to happen is that my radius is going to get larger until it reaches 3 at pi over 8. And then it's going to come back to 0 at pi over 4. So if I plot in pi over 4, that's going to look like that. I plot in pi over 8, that's going to be approximately there. And now notice I'm going to want a radius of 3. So I'm just going to draw in my circle of radius 3 to have as a reference. So now as I'm plotting points, I'm going to say at pi over 8, I have radius 3. So I'm going to start at 0. I'm going to increase until I get to that point. And then my radius is going to decrease back until I get to pi over 4, where I again have a radius of 0. So I get the corresponding picture for that graph. Now if I continue, what's going to happen is at pi over 4, I'm going to have a negative radius, which is going to get bigger in a negative direction until I get to this point where I have a radius of negative 3. And then it's going to get smaller in a negative direction until I get to 0 at this point. And so now if I'm plotting those out, here's pi over 4, here's pi over 2. So then at 3 pi over 8, I'm going to have my largest negative radius. But now I do want to be careful here is because I'm negative, I'm going in the opposite direction. So this would be negative pi over 4. This would be negative 3 pi over 8. And so right here, negative 3 would look like this. And then I would have flat. And so at an angle of pi over 4, I have a radius of negative 0. And then as I get bigger, my radius gets negative. So I'm going off in the opposite direction of these angles until I get to 3 pi over 8, at which point my radius is negative 3, so I go the opposite direction of full 3. And then I'm going to get closer to 0, and so I'm going in the negative direction here until I get back up to pi over 2, where again I'm 0. Alright, so if I continue this process, plotting these points out, noticing where I'm positive radius, negative radius, what I'm going to end up with is the corresponding graph that's going to look like this. So this will be the polar plot for r equals 3 sine of 4 theta, and if you want to see the direction, the idea is that we would move like this, and then we would have negative values, then positive values, and then we would have negative values, and then positive values, and then we would continue along until we get all the way across the entire 0 to 2 pi. And notice, the important thing to also notice here is that we didn't repeat until we got all the way back to 2 pi. It is possible that we would repeat earlier than that, but because none of the leaves repeat until we get to 2 pi, we can keep that in mind that, well, all the way from 0 to 2 pi will give me 8 distinct leaves. Alright, now that I have a graph of my polar curve, what I want to do next is find the derivative of y with respect to x for any given theta. So the point here is that if I pick, say, this theta right here, I would find this line right here, and if I wanted to find the slope of that tangent line, what would that be? Well, the slope of that tangent line is just going to be dy dx at a given point. So instead of finding it at a single point, we're going to find this in general, so let's find dy dx. Now what I want to point out is that in the last one we saw for parametric curves that dy dx can be found by taking dy dt over dx dt. So I'm going to use that same trick again, but now I'm going to think about y as a function of theta and x as a function of theta. So dy dx is going to be dy d theta over dx d theta. Now the reason why I can do that is because when we're converting from polar coordinates to Cartesian coordinates, what we can do is we can remember that, well, the y is always going to be r times sine of theta, and the x is going to be r times cosine of theta. Now, if we take the extra step to notice that r is also a function of theta, we get that y is just going to be 3 sine of 4 theta, sine of theta, and x is going to be 3 sine of 4 theta, cosine of theta. So therefore we have both y and x as a function of theta. Since we have them as functions of theta, we can find the derivatives with respect to theta. So therefore we can find dy dx. So now that we have y as a function of theta, we're going to need to find dy d theta. And so if we look here, we notice that, well, this is just going to be a product rule. We have 3 sine of 4 theta times sine of theta. So the derivative is going to be the second times the derivative of the first plus the first times the derivative of the second. If you'd want a refresher on the product rule, notice I'll have a link down below so you can look back over that. But as we look through this, we would say our second function is sine of theta, and our first is 3 sine of 4 theta, so the derivative of that is a chain rule, which if you'd like to see a refresher on that, I'll also include a link to the chain rule down below. But what we're going to get is just the derivative would be 3 cosine of 4 theta, which is the derivative of the outside times the derivative of the inside is 4. Now, we're going to get plus the first is 3 sine of 4 theta times the derivative of the second, and the derivative of sine is cosine theta. So I get dy d theta is sine of theta times 3 times cosine 4 theta times 4 plus 3 times sine of 4 theta times cosine theta. Alright, so as we find dx d theta, we're going to run into the same thing, is that we're going to have a product rule followed by a chain rule. And so the product rule is going to be, well, my first function is 3 sine of 4 theta, my second is cosine. So if I take second d first plus first d second, I get cosine of theta is the second times the derivative of the first is, well, if we simplify this, we're going to get 12 cosine of 4 theta, just like we did before, because we did do that one for dy d theta. Then I'm going to add, the first is 3 sine of 4 theta times the derivative of the second. Well, the derivative of the second is negative sine of theta. So I end up with dx d theta is cosine times 12 cosine 4 theta plus 3 sine of 4 theta times negative sine of theta. And so we'll place that in up here. And so what we arrive at is that dy dx based on theta is going to be just the given equation here. So that is, if we want to find the slope of the tangent line for any given theta, we can do that by plugging in the theta. Now that we've found dy dx for any theta, we're going to move on and we're going to say, well, can I find the area enclosed by the curve? And so now to find the area enclosed by, we'll start with one of the leaves and then we'll work on all of them afterwards. But the idea is that in order to find area, we're going to have to find an integral. And the integral is going to be, we're going to cut these into cross sections and we're going to add up the areas of the cross sections. So now if you look back at our previous videos when we looked at areas using integrals, we would cut a lot of rectangles, but in this case rectangles aren't going to be very convenient. Therefore what we're going to do is we're actually going to cut triangles, and what our triangles are going to look like are something like this. And so now if I take that triangle plus the triangle here and the triangle here, as I move along, I'll get an approximation for the area in that leaf. Now I've drawn that large enough so we can see it, so it doesn't look like a great approximation. But if we do let these change in this angle here get smaller and smaller and smaller, we will get a better and better approximation until, if that change becomes infinitesimally small, we'll get the exact area under the curve. Now, if we look at this, what we're going to get is, well, the area of each of these cross sections, or the area of each of the triangles, are going to be just 1/2 base times height, where the base is this distance here, and the height is this distance here. And so now, if I look at that, the height is this distance, and we'll go with the base is this distance. So now my base is going to be, well, that's just the radius based on the angle that I'm looking at. So that's going to be r of theta. The height now is going to be this height here. Well, that height is based on this angle in here. And so let's call that alpha for now. If that's alpha, what that height is going to be is it's precisely going to be just r sine of alpha by the definition of sine. So if I want to simplify this, what I get is I know r based off of theta, but now that alpha there, what we're doing is eventually this is going to get smaller and smaller. So what that really is that that is my change in my angle theta. So I get my height is r of theta times sine of delta theta. Now the next thing I want to point out is that if we look at sine of x, as x gets small, so when x gets small, we know that a continuous function will look like its tangent line. So if I were to find the tangent line of sine of x at x equals 0, we would get the derivative of sine is cosine. If we plug in 0, we get 1. So my slope would be 1 times x minus x naught would be 0. Y naught would be sine of 0 is 0. And so we would say that sine of x is approximately equal to x for small x's. Therefore, sine of delta theta is approximately equal to delta theta for small delta thetas. Now, since we're going to let delta theta not only get small, but arbitrarily small or infinitesimally small, not only will that be an approximation, but it'll be exact. And so what we can say is that as we let delta theta get infinitesimally small, our h is just going to be r of theta, delta theta. And so this would be a good approximation when theta is small, or delta theta is small, and it'll be exact when it becomes infinitesimally small. Now, if we combine that together, what we get is that the area of the cross section is just going to be 1/2 times r of theta times r of theta times delta theta. And so, now that we know the area of each of the cross sections, we can add up the areas of the cross sections in order to get the total area of the leaf. So in order to get the total area of the leaf, I'm going to add these all up as delta theta gets infinitesimally small. So the way I'm going to say that is the total area is going to be the integral from some point to some point of 1/2 times Well, now I have r of theta squared. And now I'm going to let this get infinitesimally small, so instead of delta theta, I'll call it d theta. So I have to find the integral from a to b of 1/2 r of theta d theta. And so now what I have to do is just say, well, what is r of theta? And what's my beginning value? And what's my ending value? And so I already know r because that's given to me. So I'm going to get 1/2 times 3 sine of 4 theta squared d theta. And now I'm going to have to say, well, where does it start and where does it stop? Is, well, if I want to look at just this leaf, so I'll fill that in. If I want to find just that area, we can go back to the work we did earlier and we could say that, well, this leaf started when theta was 0. And then we increased our radius till we got to pi over 8 and decreased it till we got to pi over 4. So because we reached 0 again at pi over 4, we would integrate from 0 to pi over 4 would be the interval of thetas that we're interested in for the given leaf. Therefore, if I want to find this area, I have to find the integral from 0 to pi over 4 of 1/2 times 3 sine of 4 theta squared d theta. Right. So in order to find this integral, what we're going to have to do is we're going to have to find the antiderivative of this function. Now, instead of working through this all again, I'm going to refer you back to one of the other videos where we work on integration techniques, but I would square this out and simplify, and I'd end up having to use a substitution, and then I'd have a sine squared in there, so I'd have to use a reduction formula. And so if I combine those all together, what I get is the integral of this is going to be 9/16 times 4 theta minus sine of 4 theta cosine of 4 theta, and then we're going to evaluate from 0 to pi over 4. Therefore, if we plug that in, what we get is that the area of each leaf is going to be exactly 9/16 pi. Now, since we found that the area of each leaf was 9/16 pi, we can say, okay, well, each leaf is 9/16 pi, so if I want the area in total enclosed, we can count up and say there are 8 leaves. So the total area enclosed by the curve would be 8 times 9/16 pi, which would be 9/2 pi. Now, also we could say that, notice that as we were integrating this, or drawing this, we didn't repeat any of the leaves until we got all the way from 0 to 2 pi. So if we wanted the entire thing, we should integrate from 0 to 2 pi, and if we integrate from 0 to 2 pi of this, well, we're going to end up with exactly 9/2 pi as well, so either one would give us the same answer in this case. We just have to, again, be careful that these aren't repeating at all, so that you might only have to go to pi to get all of them instead of 2 pi to get all of them. Thank you for joining me today as we work through some calculus problems. I hope you learned something, and I hope that helps out with your studying. If you did enjoy it and you learned something today, make sure to hit that like button and subscribe to the channel.